All right, our next speaker is Stephanie Núñez Hidalgo, Reproductive Coexistence in Epiphytic Bromeliads.
Good morning, everyone. It is a pleasure to be here this morning. This morning, I will talk about a study that my advisor professor, Alfredo Cascante Marín, and I carry out on reproductive coexistence in epiphytic bromeliads. No. Yeah. So ecosystems, planes compete for resources. And this competition is strongest between closely related species. One of the resources that planes compete for is pollination services. And among related species with similar floral traits, it is common to find some groups of plants share pollinators. The use of the same pollination vectors could involve interspecific pollen transfer and deposition. But how do plants avoid interspecific pollen transfer? Plants have a series of mechanisms that occur before or after pollination, and estimating the magnitude of these mechanisms is very important because it allows to explain how plant diversity is maintained and how sympatric species coexist. Because very diverse groups of plants, such as Bromeliaceae family, probably have strong reproductive isolation mechanisms, but we do not know. So, to understand how these reproductive mechanisms work in a diverse groups of plants, such as the Bromeliaceae family, we wanted to study the barriers that a diverse groups of plant bromeliads have in our area, such as genus Werauhia. I am going to introduce you to Werauhia. Werauhia is a genus of the subfamily Tillandsioideae, was segregated of the genus Bromeliaceae in 1995. It has about 100 species. It is very diverse. Epiphytic plants predominate in this group. And their center of diversity is in the mountains of Costa Rica and Panama. In this market area, there is our study site in the center of Costa Rica. Werauhia is mainly recognized for having nocturnal entices and inconspicuous floral coloration. Werauhia is a monophyletic group, and pollination by bud predominates. At our study site, we choose 4 species. Werauhia, Werauhia ampla, Werauhia subsecunda, Werauhia nephrolepis, and Werauhia pedicellata. These species represent the floral diversity of the genus because Werauhia ampla and subsecunda have simple inflorescence, and Werauhia nephrolepis and pedicellata have compound inflorescence. These species are the most abundant in the study site. In a preliminary study, we discovered that these species have highly self-compatible and self-fertilizing. Self-fertilization acts as reproductive assurance mechanisms because these plants have a pollen limitation, and their self-fertilization is delayed to the end of the flower's life, when there's not opportunity for cross-pollination. This bat is, we found that these species, are mainly pollinated by this bat. I mentioned before that the reproductive mechanisms can be classified into two groups. These groups may have more types of classifications. For our species, we find 4 types: in pre-pollination, floral phenology, and floral mechanical. The others do not apply because these species open their flowers at the same time and share the same pollinator. In the other case, post-pollination, we study interspecific incompatibility, also called incongruity, and hybrid vigor, related to seed production and seed viability. Some researchers mentioned that self-fertilization as a reproductive mechanism, but we have already determined that in our species, it has the function of reproductive assurance. Okay, to measure the strength and contribution to total isolation between species, it is necessary to apply a series of indices. We apply the formulas proposed by Sobel and Chen. But for phenology, we use the Martin and Willis formula. These formulas have a value between 0 and 1. If the value is 0, there is not isolation. But if the value is 1, there is complete isolation. These indices are estimated between pairs of species and reciprocally. For example, Werauhia ampla versus Werauhia subsecunda, and Werauhia subsecunda versus Werauhia ampla. The contribution value is additive and sequential in the way they occur in the life of the plant. This means that if the first barrier is incomplete, so the other barriers can contribute to total isolation. What did we find? For the first barriers, pre-pollination, floral phenology, we carry out 2 biweekly, by-month visits in 4 different periods. In general, the species have different flowering peaks. They reduce floral synchronization and the possibility of pollen transfer between species. In the case of Werauhia nephrolepis, here in red, this species has different flowering peaks and flowering periods far from the other species. In the case of pedicellata, it's a similar case of nephrolepis. In yellow, this species has a slightly overlap with strong different flowering peaks. But in the case of Werauhia ampla and Werauhia subsecunda, these species, despite having different peaks, do overlap in their flowering period. Please remember 2 species with a great overlap in floral phenology. We analyze the sizes and shapes of the flowers between species because this is related to the position of pollen is deposited on the body of the pollinator. A principal component analysis was applied using 4 variables: stem length, pistil length, corolla mouth width. This analysis separates the species into 2 groups: large flowers with Werauhia nephrolepis and Werauhia ampla, and small flowers with Werauhia pedicellata and Werauhia subsecunda. These types of analysis is common in studies of reproductive isolation, but unfortunately, no one has been able to apply this result in an index. And we are not this section, we could not. However, the floral mechanical barriers were estimated considering the position of the reproductive structures. The same position is 0 without isolation. The different position is 1 with complete isolation. Ampla, nephrolepis, and pedicellata share the position of the reproductive structures at the top. Pollen deposit, in the case of ampla and nephrolepis, with large flowers, pollen deposition is here. But these species do not have flowers at the same time. In the case of Werauhia pedicellata, with small flowers, pollen deposition is here, on the forehead of the bat. In the case of Werauhia subsecunda, with small flowers, it is the only species that had lateral structures. This condition provides isolation for the other species, especially with Werauhia ampla that has the same floral phenology. Here you start with post-pollination barriers. For these barriers, we could only perform interspecific pollination crosses between species that had some flowers at the same time. This condition excludes Werauhia nephrolepis. For the first barriers, incongruity, fruit formation indicates no isolation. Of a total of 6 crosses for the combination of the 3 species, only 3 crosses produce fruit. These values indicate a slow isolation. But of the other 3 crosses, no fruit were produced, indicating complete isolation. For the combination between Werauhia ampla and subsecunda, fruit were only produced when Werauhia subsecunda is mother pollen receptor. This means that there is unilateral incongruity. For the hybrid vigor mechanisms, we estimate 2 aspects. It is important to mention that in all post-pollination barriers, the formula considers the proportion and intraspecific crossing between interspecific crossing. The 3 crosses produce fruit, were able to produce seeds. These crosses produce seeds, were able to produce viable seeds. This means that there is partial isolation. How much do barriers contribute to total isolation between species? For that combination, the species with Werauhia nephrolepis, the isolation is complete by floral phenology. We can see this line represent complete isolation. But in the case of nephrolepis and pedicellata, it is important to mention that these species have differences in floral sizes and shapes, and that influence pollen deposition. Here we found the first barriers, floral phenology, is incomplete. So the other barriers, the second, floral mechanical, complete the isolation. In this case, it is only for the interaction, the Werauhia ampla and Werauhia subsecunda, that interspecific incompatibility complete the isolation. In most cases, the pre-pollination barriers that largely contribute to total isolation. It's the only case that pre-pollination is not sufficient, post-pollination complete the isolation. But if the values of the differences in flower shapes and size could have been included as an index, the isolation would have been complete only with pre-pollination barriers. Conclusion. Pre-pollination mechanisms were the most important in preventing interspecific genes flow, confirming the pattern previously observed in other groups of angiosperms. The result contradiction previous proposal that in the family Bromeliaceae, pre-pollination barriers the weak. Estimating the contribution of reproductive isolation mechanisms has been poorly documented in the tropics, and there was no standard way to measure it. There is information about the importance of floral mechanicals, such as the reproductive isolation. It is necessary to extend this type of study to other groups of plants with other types of pollinators. Thank you so much. My English is very bad, so I need patience.
Thank you, Stephanie. Any questions?
So that was really a great talk, and it really should be replicated on several other groups of bromeliads, several large genera. I just had one question. When you were doing the crosses between species and looking at seed set, did you also do the controls, as say crosses within species, to see what the fraction of seed set was in that case, where you'd expect high set?
Oh, I'm sorry, I don't understand. Can you repeat?
Okay. So in your study, you did crosses between different species of Werauhia, and several of them showed much lower seed set, right? So they showed substantial reproductive barriers. So that's good. My only question was whether you also, say, crossed species 1 with species 1, where the seed set should be quite high. Just to confirm that, did you do that?
interincompatibility, you have to know the success from intra-crosses. And that's the way to compare the result from the intercompatibility cross.
Any other question? Okay. Thank you, Stephanie.